Okay, I guess you can hear me okay. Well, I really want to thank the organizing committee for first letting me share the stage with such an accomplished group of people. I can only look at the future and be someone like that. And on the second hand, also for letting me tell the story of how I believe food and cooking and the science of cooking can make a case for better communication of science to the general public. But before I start, I like to thank those who make this possible, and the first and most important are my family. The time that I invested in making this presentation is time that I didn't spend with them, so I think the least that I can do is to thank them. And second, to a friend of mine, Chris Vetkovich, who pretty much was an instrumental element of making many of the animations and videos that you're going to see today. So my story begins with a lonely but beautiful egg yolk. I don't know about you, but I think that egg yolk is the best sauce in the world. There's nothing better than a saucy egg yolk sauce. So there was this chef in France that was about to close his restaurant for the week, and one of his preferred customers came by and asked for this salad. And the salad had hard-boiled egg and mayonnaise combined. And obviously, the chef very graciously agreed to make the salad. He went back to the kitchen and realized that he only had one egg left. So he faced the dilemma, do I hard-boil the egg or do I make the mayonnaise? Because he did everything from scratch. So retrieving from experience, the chef went to say, well, I use 1 or 2 egg yolks to make kind of almost a liter of mayonnaise, so maybe I can extract some of the yolk from the egg, make the mayonnaise I need, and hard-boil the rest. So off he went, took a needle and a syringe, extracted a little bit of that yolk, make the mayo he needed, and moved on. What the chef wasn't really realizing at the time is that he was using some fundamental aspects of emulsion stabilization. An egg yolk has plenty of phospholipids and plenty of proteins that can act as surfactants. So we can, in fact, make more than a liter of mayonnaise with 1 egg yolk. The limiting factor here is the continuous phase. How much water we have available to create interface, and also the mechanical action, but that's another story. So the outline of my presentation, I'm going to touch on what is the public understanding of science. I'm going to draw some information published by the National Science Foundation. I'm going to try to make a case for science inspired by the kitchen, because I know that some of you, or many of you, are not convinced of that. And then I'm going to talk to you about my recipe, no pun intended, on how successfully and effectively communicate science to the general public. The 4 main ingredients are going to be passion, visualization, embracing ignorance, and a lot of engagement. And last but not least, I'm going to ask for your participation in a formal call to action. So, a look in the mirror. When scientists are asked about how much they are engaged in public outreach, around 40% of them respond that they are not whatsoever. When they ask for the reasons why, they say that I don't have time for that, I really don't want to, and I don't care. So, where are you in this universe? Okay, homework. The other thing that happens, and this happens every day and everywhere. As scientists, we believe and we judge that when our story, when our published research in peer-reviewed journals is picked up by the media and then digested, in whatever that means, and delivered to the public, we believe that most of it is actually not error-free. And then here comes, the sensitivity. My data is not being correctly interpreted. Is not put in the right context. The conclusions have been misunderstood, and this creates just confusion with the general public, right? Of what our true message really is. But when we probe a little bit more in terms of what the general public currently is in terms of basic physical and biological knowledge, We find out, and this is just 3 of the 14 questions that the survey conducted by the NSF does. 50% of people do not know that antibiotics are not effective when it deals with viruses. 50% of people believe that non-GMO tomatoes have no genes. Okay? And 50% of people believe that electrons are bigger than atoms. So again, just a small close-up to the picture of what the public understanding of science is. A third of the population surveyed believe that astrology is sort of or very scientific. Okay? 40% of people do not know how a microwave actually heats food. They use it every day, I bet you that, but they don't know how it works. And then what was really interesting, I have to say, I was gladly surprised, is that scientists enjoy being perceived as having the most prestigious of all occupations for the last 40 years. That's crazy. You know, I didn't expect it, you know. So, but I think that's good, that's great, but it also brings a lot of responsibility from our end. Okay? Like, I don't know what's the name of the uncle of Spider-Man, right? It's like, with great power comes great responsibility. So, what if we don't do anything? You know, what if we just keep doing the things we do today? I think we're going to get into a vicious cycle, okay? And this vicious cycle means that we're going to continue doing our research, being happy in our labs, publishing data, the media comes, interprets it in whatever way they want, sends a message that we are not happy with, and then a society is being fed information that makes them take decisions based in misinterpreted set of data. And that can have lifestyle consequences. Okay? And don't get me started with examples, but you all know at least one example. So I'm going to try to make a case for science inspired by the kitchen. You know, I'm a food scientist, so I love food. That's what I do for a living. But I'm going to take it out of its usual context of food processing. I'm going to go into the kitchen. So the first thing that I want to convey is that we need to acknowledge and recognize that food is complex and very personal. So we can get into touchy discussions, but also it can allow us, the size of the reward is very big if we do it right. I bet that many of you, most of you, have gone through the disappointment of a failed recipe. You know, how many times have you tried to make a souffle, bread, pancakes, you know, as simple as pancakes, right? You put the bicarbonate too fast, that thing bubbles in the fridge while you are, hydrating the proteins and all these kind of things. And when you are putting it in the pan, it's flat. Right? So it's like, what happened? You know, I did the same last time. No, you didn't. You know, because you don't remember. So the point I want to make with this is, if we become a little bit more observant of the cooking process, we are going to discover that a lot of the principles that govern many of the reactions that we see in the lab in different contexts can be translated and can be very useful. So if we take cooking as a scientific endeavor, we can then create this and register and record our personal culinary observations. And if we continue to be devoted to this task, which is not easy, we can start now creating hypotheses on the behavior of food. And if we pursue now the experimental route, you know, having an experimental kitchen or a laboratory as a kitchen, we can create practical and relevant knowledge, not only for us, but for others. You know, I always joke, you know, with my co-workers and colleagues, you know, if I can make my mom cook better, I'm making a difference. And not because my mother is a bad cook. She's awesome, you know. But she believes things that I said, Mom, that doesn't make any sense. And let me show you how, and let me show you why. And that makes her a better cook. So if we can do that with many of us, there are rewards on society. You know, we can cook more at home more often, and that's a good thing. We can have more control on the food choices we have, and that's a good thing. We can make more affordable meals, and that's a good thing. And we can have a lot of fun, and I think that's a good thing. So, but we don't have time to do that. That's anybody's priority, no? That you define your own priorities. So, I'm going to start talking about the ingredients, no pun intended, of this recipe of successful and effective communication using science and food as conduits of the message. So I'm going to share with you a video of the late Professor Richard Feynman, which is for me one of the greatest inspirations in terms of how to communicate with the public. Please.
I have a friend who's an artist and has sometimes taken a view which I don't agree with very well. He'll hold up a flower and say, look how beautiful it is. And he says, you see, as I as an artist can see how beautiful this is, but you as a scientist, oh, take this all apart and it becomes dull thing. And I think that he's kind of nutty. First of all, although I may not be quite as refined aesthetically as he is, that I can appreciate the beauty of the flower. At the same time, I see much more about the flower than he sees. I mean, it's not just beauty at this dimension, there's also beauty at a smaller dimension. I could imagine the cells in there, also the processes, the complicated actions inside, which also have a beauty. The fact that the colors and the flower evolves in order to attract insects to pollinate it is interesting. It means that insects can see the color. It adds a question. Why is it aesthetic? All kinds of interesting questions which the science only adds to the excitement, the mystery, and the awe of a flower. It only adds. I don't understand how it subtracts.
So this video is very touching to me. You know, it really, one thing that is important as well is that people tend to believe that because we do science, we have no appreciation for beauty. We're these cold-hearted individuals that see things as they are data, right? Show me the data. Give me the evidence. And I think that this also uncovers a great opportunity for us as we communicate with others. Show them how passionate you are about what you do. Because I assume that you all love what you do, right? Apparently not. But I love what I do, you know. So, and I think that if I'm able to convey that passion to others, they might get a little curious and get to know a little more, you know. So tell me more about that egg thing that you were talking about, right? And then it will be up to me to provide the right context and the right terminology for them to understand. But again, if you do it with passion, I bet you they will come back, you know, and they will go back home and do the experiment that you told them to do, and they will come back, you know. So, and I'm going to show you an example of this passion of mine. I showed you already a picture of a lonely egg yolk, so I want to bring her back to the picture so she doesn't feel that lonely. This is Hervétis. Hervétis is a very well-known French physical chemist, self-proclaimed the father of molecular gastronomy. We're not going to talk about molecular gastronomy, we're going to talk about the yolk. He holds in his hand what he calls the 65-degree egg yolk. So I'm going to give you just a few seconds to read the statements there, but basically the summary of his statement is cooking egg yolks sous vide, and I'm going to go into what sous vide is. It's not a matter of time, it's all a matter of temperature. The thickening process of an egg yolk cooked sous vide has nothing to do with time, and I was like, that kind of doesn't make much sense to me, right? It's kind of oversimplified. So, cooking sous vide, you know, the sous vide technique is basically cooking foods, eggs in this case, but you can, you know, cook pretty much anything, at relatively lower temperatures compared to the boil. I'm talking about 60 to 70 degrees Celsius for most meats and 80 to 85 degrees for most vegetables. And basically what this allows us to obtain are textures that through normal cooking processes such as braising, poaching, and roasting are very difficult to achieve or actually impossible to achieve. So it does add value to the repertoire of the chef, but also of the home cook, right? So I said, let's see if he was right. Maybe I was wrong, because I can't be wrong. So this graph, and the principle that I want to illustrate here is protein denaturation as a discrete or continuous phenomenon. Is protein denaturation an on and off switch? Because that's what we tell people, by the way. The temperature of denaturation of beta-lactoglobin is 62. You know, we have it like here, 62. Well, for egg yolk, there is a little of a different story. So this plot, what it shows is on the y-axis is the tan delta, which is a parameter used to measure the elasticity of, in this case, the egg yolk. And on the x-axis, we have the total isothermal cooking time. So when I put the egg at different temperatures, how long I waited for the process to occur. So here, using the pointer now, what we demonstrated is it doesn't matter what temperature you cook the egg at. It will gel, so it will cross tan delta of 1. And if you let it there, it will continue to thicken, to produce texture, to build structure. So very simple experiment. There is a lot behind this experiment. I'm not going to go into those details. You can read them in the citation here. So I was very happy proving somebody wrong. But then I said, so what? You know, what is the practical application of this? How can my brother, who doesn't cook at all, cook better? Let's give him an excuse. So this is what happened. We cook eggs on shell, in the shell, and we follow the texture of the egg yolk as a function of time for different temperatures, different times. What we saw is that for every single temperature, the increase in viscosity at 10 reciprocal seconds, which is the shear rate that is related to in-mouth behavior of food, was linear. So we said, oh, maybe there is something here. Maybe we can start predicting some stuff. But I wasn't going to go and tell the chef, because at the end, a big part of my audience are the chefs. Hey, can you cook me an egg yolk to a viscosity of 30 Pascal seconds? Well, you already know what reaction he or she is going to have. So I said, I have to develop a way to communicate the finding in a way that is completely understandable and actionable. So this is what we did. We went to survey a series of thick edible fluids with increasing viscosities at 10 reciprocal seconds. Okay? Now, this is shear viscosity only. It doesn't take into account shear thinning behavior. So for those who are already thinking ahead of me, so, you know, from whipping cream all the way to Marmite, raw egg yolk is a little thicker than whipping cream. I didn't know that. And then this is the end result. This is what is actionable. And this is now, this plot, as you see it, is being used in many kitchens around the world and by many cooking amateurs. Okay? So basically, if you want an egg yolk that has the texture of sweetened condensed milk, all the chef has to do is to cook it at 62 degrees Celsius for about an hour. But if you don't like runny yolks, you like something a little thicker like honey, but you have to wait a little longer at 62. But if you really want it set, but not dry, like Marmite, well then, have 5 hours. So 5 hours is like, Jesus, you know, who has 5 hours? You know? It gets worse. When you cook a piece of pork belly sous vide, you are in the order of 60 hours. But again, it's not that you're waiting there looking at the piece of pork belly to change, right? You just go on with your life. So the same applies here. But again, let's assume that you come to the restaurant and tells the chef, he tells you at the beginning of the meal, how do you like your egg yolk? I said, like Marmite. Come back in 5 hours. No. He's going to cook it probably at 67 for around 40 minutes. And he's going to give you exactly the same texture. So the value of the graph, the value of the model is that you can now predict. Okay? You just need to know what is what you want. That's all we need to know. And it's based on a systematic understanding of this denaturation process in egg yolks. Now, the other thing is all of us have different ways in which we learn. Some people like to see things, some people like to hear things. I like to see and to write. So I'm going to help those who learn like me. Visualizing. To do that, I want to talk about ice cream. Ice cream is one of my passions. I have too many passions. When I think about ice cream, I think about a cone of ice cream with a scoop of dark Belgian chocolate. Ice cream. Delicious. But if I get going with the thoughts, I start to see the microstructure. Okay? So the fat globules, partially coalesced, with the air bubbles and the ice crystals, la, la. But if I really get going, I see the math of ice cream. And this is a fact, this is true, believe it or not, published in Trends of Food Science and Technology. This equation, which is based in the complex dispersed system formalism proposed by Hervétis, describes an ice cream that is at 10% fat, 100% overrun, and minus 20 degrees Celsius. That's the condition for an ice cream of such composition. Okay? So you want to know more about it, there is the citation. Now, if I want to talk to you about ice cream, I need to tell you how it is made. Right? And again, please put into context the fact that I'm trying to send the message about ice cream to the general public. So I'm not dumbing down the scientific principles. I'm just trying to make them more digestible. So the science is not as heavy as you would expect it to be. But to tell you about ice cream, again, I have to tell you how it's made. So I hope you all signed the non-disclosure agreement at the entrance of the door, because what I'm going to tell you is a trade secret. Okay? So this is how ice cream is made. Okay? Anything you have heard before, it's not true. Okay? Now, when you visualize ice cream, you can deal with this. So we need tools. We need tools. You know, I don't have all the answers, so I need tools that can help me visualize the big picture. Knowledge mapping comes to rescue. Knowledge mapping is a technique that allows us to understand complex relationships, brings forward cause and effect. And it also builds on multiple lines of reasoning, and by doing this, makes explicit what is implied, so there is no ambiguity in the message. What I'm showing you is what it is. There is nothing, you know, there is no secret around. So let's walk through an example. Knowledge mapping is based on facts. And facts are assertions that can be proven by experiment, observation, or demonstration, such as lactose is found in milk, milk is added to ice cream. And based on this, we can create a very simple line of reasoning. Okay? But no, you know, life doesn't give us facts as bullet points. We have to extract them. So from this text, right, significant ice structuring protein, ISP, activity was observed in delaying ice crystal growth in all solutions containing 0.13% total protein from acclimated winter wheat extract. From all that, we extract the meaning, and then we can create a graphical representation. And this is the relationship between the two entities. This is a very simple map that I extracted from a paragraph of the publication, again, where it shows you the different relationships among the different elements of the map. So again, I'm just giving you what you need, the essence, okay? So then one day I said, can I do this for ice cream? And this is what I got, okay? So it's a mess, I know. Only I know, and I struggle when I look it back in time, so like, what the hell was I thinking? But ice cream is at the core. Ice cream is a three-phase system, very complex food, where ice, a foam, and an unfrozen phase coexist. So can I do this on a friendlier way? Can somebody else that have no notion about ice cream be taught what ice cream is? So I went to do this sort of graphic representation, you know, where ingredients, properties, building blocks, and processes now can be coming to the picture. And this is what I got the first time I did this, and this was years ago. I'm going to go very quickly through it. You will see it several times, so when you get out of here, you can be an ice cream expert. Proteins emulsify the fat. Aging hydrates the protein and crystallizes the fat. emulsifiers displace the protein and prepare the fat. Whipping makes the foam and restructures the fat. That fat stabilizes the foam. Hydrocolloids, sugars and proteins enhance the viscosity. That viscosity controls the foam and lengthens the melting behavior. The foam softens the texture, enhances the body, and sugar depresses the freezing point. And by depressing the freezing point, we jump into the ice phase of ice cream. So, a better picture. Then I asked a friend of mine to help me with this, representation, and this is exactly the same. But I think it's even friendlier. Everything I just told you is being animated. Thicker lines represent more important processes. Red lines represent absolutely fundamental processes in the creation of the foam. Okay? So, kind of getting there. And then the next video is, I asked my friend Chris, can I just jump into an ice cream mix? Like, what if I, make myself 2 microns tall and went into an ice cream mix and see what's going on? So I can, again, I'm thinking about my final audience. So this is the video that came out of that. This is a fat globule, many fat globules. These are casein micelles from milk that we need to stabilize the emulsion that will make the ice cream. Okay? So we homogenize, and that protein emulsifies the fat. It deposits on the surface of the globule. And again, this is an important step that many people are not aware because they use just cream to make ice cream. It's already homogenized. We age that mix in the refrigerator, and 2 things happen. One thing that is very important is the fat crystallizes. And you can see here a crystal already protruding from the surface of the globule, and many crystals are starting to protrude. Fundamental to ice cream making. You cannot make good ice cream with oil. You need crystalline fat. Low molecular weight emulsifiers such as mono and diglycerides or polysorbate 80 then comes and displays those casein micelles from the surface of the globule and get it naked. Okay? And that's very important because when we start whipping the mix to make the ice cream, to incorporate the air, what happens is that the fat globules start to collide against each other, piercing one another with those crystals protruding from the surface and partially coalescing. And then they deposit on the surface of the air bubbles that we put in there, stabilizing the foam. Okay? And then Chris couldn't, again, this is representative of ice cream. There is no ice. It will come later. But this is what happens with whipping cream. And then my friend wanted to pick on me and created my own brand of ice cream, with 90% more science. So there you go. Next slide. So that takes care of visualization. How can I help people visualize in their minds what I'm talking about? The third thing is embracing ignorance. I don't know about you, but it bothers me a lot to meet scientists that are not capable of accepting that they don't know. Okay? So, and I'm going to open myself to you and letting you know that I don't know many things. And the example of the things that I don't know has to do with egg white. So I love eggs. I know a lot about egg yolks. I know quite a bit about egg whites, but I actually don't know much about egg whites anyways. And I bet you I've made more meringues than all of you combined. Okay? And I still don't know much. The purpose of this slide is just to illustrate how complex egg white is. 6 different proteins at different levels, with different isoelectric points, different molecular weights, different denaturation temperatures, if we are going to believe them, as I already demonstrated with egg yolk, and a very complex chemical environment with regards to disulfide bonds and sulfhydryl groups. What is going to be key here is that ovalbumin is the only one of them that contains free sulfhydryl groups. So that brings me to the meringue part. Those of you who can recall making a meringue probably will know that usually we are advised to use cream of tartar, lemon juice, or vinegar in making them. And it makes a huge difference. It actually works, right? So if you don't do it, do it, you know? But why? What's going on? What's the mechanism? You know, I want to know why and how. Maybe how better than why. So thanks to people like Harold McGee, Shirley Corriher, with whom I will be making a demo related to this tomorrow, you know, they have advanced our knowledge of the science of cooking driven by curiosity. And they have come up with this explanation, particularly McGee. You've probably already read much of this, but basically alkaline pHs promote the super and faster aggregation of albumin molecules, which at the end create this graininess in meringues and make the foam to collapse. If we add the compounds that I just mentioned, or the ingredients that I just mentioned, the pH goes to 7, and the equilibrium of this reaction is tilted in the opposite direction, and you can really whip for as long as you have patience for an egg white mix, and it will not get grainy. It will not. Okay? So I said, okay, this is very interesting. So they're telling me that I'm blocking disulfide bond formation, but I'm also changing the pH. So because I have this combination of proteins with different isoelectric points, is the isoelectric point of the proteins also related to the functionality that I observe? So I said, how do I demonstrate that is one thing and not the other, or both? So I said, let's block the thiol groups. And these were the 3 compounds that came to mind in my very limited experience with these compounds. I chose NEM. Many of you already work with it, you know how stinky it is, and how non-friendly to health it is. So I said, okay, let's do the experiment. Only once. And this is what we saw. We have 3.5% raw egg white in water. Why did I dilute? To see the effects a lot faster. You know, I was very impatient. A control at pH 9, cream of tartar, pH 7, NEM, pH 9. We whip them under the same conditions for the same amount of time. The overrun, or the amount of air incorporated, didn't change or wasn't significantly different. But the amount of water or drip from the foam as a function of time in 30 minutes was dramatically different. Dramatically different. I knew this was going to be better. I thought this was going to be like this. But in reality, it was much, much more stable. And the texture of the foam was like shaving cream. Amazing. Completely amazing. Especially after only 5 minutes of whipping. Okay? So I said, if I want to continue working with these models or with these systems, I need to find an edible alternative. If I want to make it relevant to the public, right? So reading a book called On Garlic and Other Alliums, and this is going to link the talks of Professor Shiverly with mine, I found out that Allicin, it's actually a pretty good thiol blocker. And I said, hey, I get out of my couch, went to the grocery store, bought 2 kilos of garlic, asked my wife to peel it. No, just kidding. I peeled it. I made juice with it and put it in egg white and get whipping. Well, this is what we found. So the drain of the foam as a function of time, bigger drain, less stability, 10% egg white control, 1.5% cream of tartar, dramatic difference, garlic juice, no drip. So I know that you might not be inclined on eating garlicky meringues, especially after what Professor Shiverly told us. I was so disappointed. So I have no case anymore. So, what's next? Next is an open invitation to any of you who want to contribute. Why? Because, it's not shown here, we also went to buy dietary supplements with Allicin, and we whipped some meringues. And what we noticed was, directionally, we see similar results compared to garlic juice, but not as dramatic, okay? Actually, it's not here, but the curves are on, like here. So either of two things are happening. It's a fraud, right? I'm not getting Allicin in my dietary supplement. Or there is more to the garlic juice story than just Allicin. I haven't measured either of them. I haven't measured Allicin in either of the compounds. We have repeated this experiment numerous times, so we know it works. And actually, tomorrow in the demo with Shirley, we're going to be demonstrating this. So again, this is my I don't know, and I wish to know more, because chefs are already telling me. So if this does work with garlic, what about onions? What about chives? What about shallots? What about wasabi? What about ginger, galangal? I said, I don't know. Let's go and try. But one of the things that I don't like to do is cook and look, right? This experiment was hypothesis-driven, in case you didn't notice. But one of the things that I tell chefs is that you cannot cook and look. You cannot go on tossing things around and see what sticks. And I tell the same to my people working in the lab. You have to be in the hypothesis-driven mode. No cook and look, please. The last part of my presentation, I'm running out of time, is about engagement. My mother used to tell me, well, she's still alive. My mother tells me, if you don't complain, don't complain. And she's right. I already showed you some statistics around, how the quality of the science communications based on peer-reviewed journals, how it is delivered to the public, and that is not error-free, and that some of us are not engaged, and how the public, how much the public knows about basic factual things of life. So engage, right? And the way I engage is very simple. This works for me. I co-edited a book entitled The Kitchen as Laboratory. Has nothing to do with the title of my presentation, I promise. But basically, it's a compilation of essays written by scientists that are leaders in their area of specialization that touch in different aspects of the science of food and cooking. From simple, foods like a grilled cheese sandwich, where the author touches on why some cheeses work and some others don't, and why. Professor Kirschenbaum here in the audience, he wrote a chapter on stretchy ice cream. Can you create a frozen system that is as stretchy as a marshmallow? Yes, you can. How? Talking about bitterness and coffee, there is a group in the Netherlands that work on how to remove the bitterness from coffee through simple partition coefficient fundamentals, so that you can have a load of coffee flavor without bitterness. So things like that. And the other thing that many of you, I'm sure, do is engaging in social media. I'm on Twitter. I engage. I express my opinions, which are mine, not those of Mars Incorporated. And many other ways, blogs and et cetera, et cetera. So engage. So I'm going to finish my presentation with a call to action. I already expressed to you the ways that I try to do this. Be passionate. Don't be shy in expressing how much you love what you do. Uncover dimensions that are unknown to others about the beauty of what you do. Get excited. Don't be shy. Help people visualize, make stories, create analogies that work, right, in delivering the message. And try them with your kids or your brother or somebody that actually absolutely doesn't care about what you do, but you will make them care because you are passionate about this. And the last, embrace ignorance. It's really the fuel that keeps us going as scientists. So show that, and I think that the perception, again, that is already good. We are the most prestigious occupation out there. It can be reinforced. I think there is only good coming out of it. And with that, I want to thank you for your attention, and I cannot believe that I made it in 40 minutes. Thank you very much.